course, to just measure each state individually. And then we have to correspondingly adjust the error terms. Now, it's quite easy to see that this is not the best thing we can do, right? Instead of measuring each quantum state independently, we want to instead do a joint measurement on all of these states. And we do know that this will usually give us a better error performance. Now, I've just talked about these two error terms independently, but we often want to give different priorities to these error terms. And this is just some basic definitions. We can look at this in either a symmetric way, where we give equal priority to both of the error terms, and we just want to minimize their sum. And if we look at this asymptotically, this is usually gives rise to Chernoff bounds, or it's called Chernoff bounds. Or there's an asymmetric setting where we just fix one of the error terms to be small, and then we want to see how far we can minimize the other one. And this is usually asymptotically, this is called Stein's lemma. And there are two more, but I don't want to go into too many details here. For the rest of the talk, we're going to consider the second setting, or mostly consider the second setting, the asymmetric case, and going to Stein's lemma. So, and for this case, let's look at the definitions a bit more closely. So let's now say we have many copies and we want to do asymmetric state discrimination. Then in the first line, you can see the definition of what we call an error exponent. And this we get because it's quite easy to see that the error is going to decay exponentially if we take more and more copies of our input state. So now we take the error beta in the formula and the first formula on the slide, and we take minus 1 over n log beta to get the error exponent, at the same time restricting alpha to be always smaller than some constant. And I will often, now different to the past slides, I will put this index n on the error terms to indicate that we have n copies of the channel, of the state, or of the object we discriminate. And the supremum over S is a supremum over all possible strategies. So we want to find the largest possible error exponent for a certain setting. And of course, in the state discrimination case, the supremum over S is essentially just a supremum over all joint measurements. Now, to kind of get the ultimate rate, we take a limit of n to infinity, and we have to, in some cases, be a bit careful whether that limit exists or not. But generally, we are interested simply in the limit of n to infinity. And sometimes those two rates, we can't necessarily prove that they're matching. There might be correction terms based on the value of epsilon. And in those cases, we also take the limit of epsilon to 0. Now, the main result in kind of the asymmetric state discrimination is Stein's lemma, or the quantum Stein's lemma, which tells us that this error exponent is always equal to the relative entropy, which you can see on the very last line of the slide. And this is indeed the kind of result that we are looking for also in the other settings. It's a simple description of the error exponent. And we know that it's achievable and it's optimal. So this is kind of the ultimate limit at which you can discriminate to quantum states asymptotically. Now from here, let's move on to looking at channels. And of course, we can kind of do the same thing with channels. Now, just we have to make sure that we also take into account the input states of the channel. Now, if I optimize over input states rho, and I optimize over measurements on the output, And we have learned from the state discrimination case that collective measurements are usually better than just product measurements. So from now on, we always use joint measurements. Now, this again is a particular instance of a channel discrimination strategy where we use product states. So I call this a product strategy, and it's quite easy to see as an extension of the state case that for this quantity, the optimal error exponent is the channel relative entropy. And this is simply defined, as you can see on the very bottom of the slide, as optimizing over input states to the channels, or one input state to both of the channels, and then taking the relative entropy of the output states. And we do take into account reference systems here. That might be helpful. Okay, this is kind of the base quantity, this channel relative entropy. Now, as we have seen that joint measurements are better than product measurements, you could want to do the same thing with the states. You would expect that joint input state is better than product input states. And indeed, that is the case. Now, the optimal error exponent under these, what we call parallel strategies, is the regularized channel relative entropy. And this is simply the definition from the last slide, just that we have to evaluate it on n copies of the channel, and then we take n to infinity, and we normalize by 1 over n. Okay. And this is already, well, first I should say, we know actually that this strategy is in some cases strictly better than the product strategy. And this was only proven very recently by Fang et al. Now, you could hope that we made everything like joint states, joint measurements, that this is kind of the best thing we can do. But a priori, this is not clear at all, because we haven't really taken care of the structure of the channel, meaning that we can choose input states also based on previous outcomes. So for example, I could take the outcome of the first channel and reuse that to somehow prepare a useful input to the second channel. Okay, and these could potentially be much more powerful strategies. And these strategies we call adaptive strategies. Now the picture looks a bit different. We start on the left with an input state, and we first send one part of that input state through a channel. And after we do that, we use everything we have at our disposal to create a new input state for the next channel. And you can see that these strategies are more general than the parallel strategies on the last slide. But for a long time, it wasn't clear whether these are more powerful or not than any of the other strategies. And there's only recently been progress on this question, almost about the roughly last 3 years. And first, it was shown by Wilde et al. That the error exponent in this case is actually upper bounded by the amortized channel relative entropy, which is here in equation 1. And for this quantity, you take the supremum over actually 2 different input states to the channels, but then you have to subtract kind of the discrimination power you get from choosing different input states. So this was an upper bound, and then about a year later, if I remember correctly, Wang and Wilde showed that this is indeed an achievable rate. So this kind of determined the optimal error exponent in the case of quantum channel discrimination, or in the quantum Stein's setting. But it was only until later that Fang et al. Showed that this amortized channel relative entropy is actually equal to the regularized relative entropy. And a direct consequence from that is that adaptive strategies are actually not more powerful than the parallel strategies I showed 2 slides ago. So simply preparing a joint input state and a joint measurement turns indeed out to be the most powerful thing you can do in quantum channel discrimination, all through you have all these adaptive strategies as a possibility. So now we should we have all the materials that we need to look at the networks. And how do networks actually distinguish themselves from just being quantum channels? So we want to look at a priori very complicated structures, but of course, okay, here's a very schematic depiction of a quantum network. And we just assume that we somehow want to send information from the left to the right of the network. And of course, now you could just collect all the inputs and use them as a joint input and all the outputs as a joint output and essentially handle this as a quantum channel. But the main difference is that if you check like in the upper part in the middle, there are these what I call access points, which are points in the network where you can retrieve information from it, you can process it in some way, and then you re-enter it into a later part of the network. And this is what mostly distinguishes this setting from the channel discrimination. And yeah, we usually, I think this mostly goes back to work by Hirche et al. And we usually think of this in the setting of K combs. So you can see that this, for example, is a free comb. And yeah, I think you see directly why it's called that. So any network that has this successive structure, we can describe it in terms of these combs. And for the rest of the talk, I want to look at a very particular example, which is a 2-comb. And although all the results can be in some way extended to arbitrary K combs, the 2 combs actually, yeah, they take all the important features and just put it in a slightly more easy to handle setting. So a 2-comb I depicted here, and they're often also called superchannels, and that is because you can think of them as taking a channel N from A to B as an input and returning to you a new channel that goes from C to D. Okay. And one of the main results by Hirche et al. Was that we can think of any such superchannel as simply a decomposition of 2 CPTP maps. I call them usually E and D now in the superchannel case. And one, you can kind of think about it as the encoder of your quantum network, and one as a decoder, and they communicate via an additional system or reference system S, which I might also sometimes call a side channel. Okay. So this is now the framework in which we want to do discrimination. We're going to have many copies of these superchannels or 2-combs, and we want to extend the known discrimination setting or Stein setting to this approach. And now the easiest thing you can do again is some kind of a product strategy. And for this product strategy, you choose an independent input to each of the superchannels or networks. And now you optimize over quantum channels that sit in this network. So these are kind of my access points, and I have someone at the access point who is helping me discriminate the channel by putting the most useful map he could possibly put. And then we take all the outputs and we use a joint measurement. And it turns out that the optimal rate is what I define as the relative entropy of superchannels. And this is in some way just the direct extension of the channel relative entropy. Just that now we also optimize over all the input channels. Okay, and how do you prove that this is the optimal rate? That is actually not very difficult, because now if you fix an input state and if you fix an input channel, then the output states of your networks are essentially IID states. So we can just use the theory of state discrimination to get the optimal rate. But as you have seen before, it's never optimal to choose things in a product way. So the more natural way is, for example, to also choose all the input states as joint states. And indeed, we get now we get an easy result with the discrimination or with the error exponent in the setting. And the setting is the result is simply a regularized version of the superchannel relative entropy, just that we have to take now joint states into consideration, but we still have product channels. And why do I even bring up this case? It's an easy extension of the channel discrimination setting, in the sense of now if we just fix the input channel n, then we essentially have the problem of discriminating n IID channels. And that way we easily get the error exponent. And as in the as in the channel discrimination setting, we also see that this is equivalent to an adaptive strategy, where which is the direct extension of the adaptive strategy in the channel case, where we choose one input state, and then after every use of the channel, we choose an adaptive. We choose some adaptive channel to prepare the input state to the next channel. And actually, this is maybe not 100% accurate. The ends and the channel inputs in this kind could also all be different. We can also choose those ones adaptively. So now we have chosen the states. Well, sorry, I should say explicitly that these adaptive strategies are equally strong as the parallel strategies. And this follows from the channel discrimination setting. So now we can just continue our theme of making everything a joint strategy, and also make the input channels joint input channels. And this is what I call a fully parallel strategy. So now these lines on the picture on the left denote that all these channels, these input channels, are actually connected and are one input channel. And what we get is a regularized channel relative entropy, superchannel relative entropy. Now where really every part is considered to be a joint input. And so far, everything seems like rather straightforward. Also, the proof for this one is kind of still standard, or uses standard techniques. But now you have seen on the last slide that that the specific type of parallel strategies was already equally powerful to some adaptive strategies that used to be the most powerful ones in the channel case. So this is now where it starts to become really interesting, because these fully parallel strategies, they seem to be in general more powerful than the adaptive strategies that we usually use. So somehow we have to, so either we have to accept that these are actually more powerful in the network case, or we have to find more powerful adaptive strategies. And to look at that, let's have a closer look at these fully parallel strategies. And I hope now this animation is going to work. Yes. So we reorder these strategies and just bring them in a different form. Let's maybe look at this again, just briefly. So we start with the fully parallel strategy, and I'm not changing anything here about the structure of the problem. I'm just reordering the problem. And now you can kind of see that this gives rise to a different adaptive strategy. But it's not one where we put one channel behind the other channel, but we put them all within each other. And every time here the lines cross, essentially, this is where we allow for arbitrary operations that we can adaptively choose. And now this approach gives rise to a new type of adaptive strategies, which I call a nested adaptive. Yeah, nested adaptive strategies, where we concatenate the channels in some way, or the networks in some way, and allow for all these intermediate adaptive CPTP maps. And this is also where it gets much more complicated to prove results. But one of the main results is that even for this strategy, we can still get a converse bound, which is the amortized, or what I call the amortized superchannel relative entropy. And this is defined on the very bottom of the slide. And the structure is kind of similar to the one in the channel case, just that now each of the terms here kind of represents the distinguishability of a channel, or of two channels. Meaning that the quantities we look at from the start are the amortized channel relative entropies. And we take the amortized channel relative entropy of the output of the two superchannels, given that we input some different maps here, but then we have to subtract in the end kind of the distinguishing or distinguishability power of these two maps that we input. Okay, so the structure is somewhat similar to the regularized channel, channel relative entropy, but we raised it by one level in some sense. Now we can show that this is a converse bound. So the Stein's lemma setting, the optimal rate can't be any higher than this quantity. But the only thing we can say for sure for now on the other end is that this strategy has to be more, or can be more powerful than the fully parallel strategies that I showed before, which give rise to the regularized network relative entropy. And of course, the most desirable thing would here to make these two inequalities into equalities. And I've not yet been able to do that fully, but there's a conjecture, or in fact, it's not really my conjecture, but Andreas Winter proposed in 2018 the conjecture that you see here on the top of the slide. And the right-hand side is a quantity that we already introduced. It's a regularized channel relative entropy. And the left-hand side is essentially the same quantity, just that now we replace the relative entropy by a different quantity that is called the smooth max relative entropy, which is denoted by a smoothing parameter epsilon and the max on the left side. So Andreas Winter conjectured that these two quantities are asymptotically actually the same quantity. And there are several reasons for assuming that this is actually true. Most importantly, that if we look at the equivalent problem for quantum states, then this turns out to be true. We just haven't been quite able to figure out if it's also true for quantum channels. But in some way, you would assume that it should be. Now, given that this conjecture by Andreas is true, I can actually prove that there exists a chain rule. And this chain rule allows us to take like a super channel acting on a channel acting on a state with, in both arguments, the parameters being different, to like take away step by step all the elements in the quantity on the left-hand side. So we first take away the super channels acting on the system into a regularized relative entropy. And then we can also take away the channels and we are left with just the states. And this is a generalization of a result I mentioned earlier by Fang et al., in which in which work they proved this for just without the superchannels. They had it for channels acting on states. And having this chain rule, it's actually quite easy to show that the two quantities I discussed before on networks, they turn out to be equal. So the amortized superchannel relative entropy and the regularized superchannel relative entropy would be equal, given that the conjecture by Andreas holds. And if that is the case, then also for the network discrimination setting, or for the superchannel discrimination setting, we know that adaptive strategies, or these nested adaptive strategies, are equally powerful to the fully parallel adaptive strategies. Let me just take time. Okay, I should be done in about 5 minutes. That's good. Now we have explored all these different strategies, and up to one conjecture, we have determined the optimal rates. But as it turns out, you could, if you keep puzzling around with these networks or superchannels, you can even still find different strategies. And as one example, I want to give what I call here braided adaptive strategy. And interestingly, it's somewhat not clear whether these are a subset of either of the other adaptive strategies I have provided so far. And it's also not clear how to put them into that framework. So we would like to still, if you want to be as general as possible, we still have to handle these quantities separately. And now to really make a sweep for all of the possible strategies, what we define is somewhat a fully general adaptive strategy. And as I said in the very beginning, you can think of superchannels as taking them apart into encoding and decoding operations. And now to really cover all adaptive strategies, we do exactly that. And each of these gray blocks now is one part of a superchannel. And for the strategy, we allow it to pick any order, or we allow ourselves to pick any order of these parts of a superchannel. So for example, well, okay, I should also say, you limit yourself. I mean, there's a natural limitation that superchannels have to, or the parts of a superchannel have to appear in the order in which they also naturally appear in a superchannel. So I can't use the second part of a superchannel before the first, but I can at every given stage decide if I want to finish a previous superchannel or if I want to start a new one. So that means if I look here from the left to the right, I always have to start with the kind of encoding operation of a superchannel. But then for the second map, I can decide if I want to, for example, finish that first superchannel and put the corresponding decoding operation here, in which case the start would be similar to the successive adaptive strategy from the very beginning, from the channel case. Or if I start a new superchannel here in some way and put another encoding operation here, which would, for example, be the start of the braided adaptive strategy from the last slide, but also from the nested adaptive strategy that we discussed in the middle. And that way I can go through the whole block, and eventually I have to end, of course, with a decoding operation, but I have a lot of freedom in between. And for this case, like for this really most general case, we are also given a converse bound, which is a star amortized superchannel relative entropy, which is essentially defined as the amortized superchannel relative entropy on the last slide, just that we have this additional operations, these addition channels n bar and m bar that act already before the superchannel does anything. Okay, so this is a quantity that is for sure it's larger than the ones we discussed before, but it gives a converse bound on every possible adaptive strategy. And unfortunately, I can't really present any results here in terms of achievability, because it remains still very open if like any strategy you might be able to form, like a braided strategy, could potentially be more powerful than the strategies we discussed before. And this is actually the most interesting open problem that we are left with, to kind of see if this gap can be closed. So either find a sharper converse bound here, or indeed find that it's achievable and that we can outperform all the parallel strategies. Okay, so to kind of end the talk, I want to just briefly talk about some more material that you'll find in the paper. And one direction is, of course, to look at special cases. And we discussed, for example, classical superchannels, where interesting all these quantities collapse. So for all the examples I showed you so far, you can show that the simple strategy of product inputs and product channel inputs is actually optimal. And even the most general quantity I showed you on the last slide, it will not provide you any advantage. And then there are certain other examples that I just list here, replacer superchannels and certain parameterizations of superchannels that somehow reduce the complexity of the problem and allow us to give more bounds and show that certain strategies don't outperform other strategies. Then we also look at extensions of the problems. And let me just go quickly through this. I talked about everything so far in terms of relative entropy, but in fact, we don't use many properties of the relative entropy. So you could find equivalent results also for many other divergences, like, for example, the sandwich-Rayleigh divergences and so on. And we state our results in terms of meta-converses that allow us to think of it in all kinds of different divergences. And using these results, we can also find converse bounds for all the strategies for other discrimination priorities, like priorities of the error terms, like Chernov's bound or the strong converse exponent, also known here as Han-Kobayashi bounds. And of course, we extended to the setting of K-combs, so like the actual networks with multiple access points. And on the last slide, I just repeat some of the open problems. It would be very interesting, of course, to prove the asymptotic equipartition property. So that was a conjecture by Winter that I mentioned a couple of slides ago for the smooth channel max relative entropy. And we really want to learn more about the star amortized quantity, whether it's actually bigger than the usual amortized quantity, or if there's some room for improvement in the rates. And then finally, of course, more applications and looking at restricted settings, like, for example, distributed hypothesis testing. But yeah, that's all I wanted to say. The paper is not out yet, but it should be on the archive in the next couple of days, I hope. And yeah, thanks for your attention.
Okay, thank you, Chris. Any questions? Chris, I have one question. So if I remember correctly, even for discrimination of classical quantum channels, there are still open problems. For example, do we know that the Chernow bound we obtained so far is optimal or not?
If I remember correctly, we do not know that still. The Chernow bound is somewhat the quantity that has been most elusive from the ones I mentioned here, I guess. So yeah, you're right. For the Stein's lemma and so on, for the classical quantum channel, we do know the optimal rates in the channel discrimination setting, but we don't know them for the Chernow bound. I think for the Chernow bound, we know them up to a factor of 2. Okay. Like there's a discrepancy. And also here in this work for the networks, I give converse bounds, but it's not clear if they're optimal.
Okay, so do you think what's the most difficult part for proving the optimality, in your opinion?
I think in some, yeah.
Yeah, it's like the AEP conjecture by Winter, or do we need more advanced techniques to attack that open problem?
So I mean, yeah, it's a good question. So we actually don't have a good idea how to prove these results in the channel setting, and in fact, it's not even clear which side we would still have to improve. It seems like there's a very good chance that, or I think you can even see that adaptive strategies might actually give you an advantage for the symmetric setting, or there's certain evidence for that.
Okay.
And it seems to, or it might be in some way related actually to the conjecture by Andreas, but not so much the result itself, but more the tools you use. That you have to go over the Paz-Rainey relative entropy. And if we understand better how to do that, then there might be a way of attacking both of these problems, like some kind of chain rules for the Paz-Rainey relative entropy.
Okay, I see. Okay, thank you, Chris, again.
Yeah, thank you.
Hi, Stasia, can you hear me?